Hello, my name is Arturas and welcome to Code Launch. And today we're going to be talking about higher kind of types, what those things are, what problems do they solve, how they are useful, how we can use them in our code bases. And because C# natively does not support them, some other languages, like for example Scala, does, but C# does not. Java does not as well. But thankfully, we can simulate them at least in a bit of a limited case sense, but we still can simulate them and use them and take advantage of them in our code bases when we're writing C#. So how did I really, what problem do they solve? Because what they are, we're gonna kind of discover along the way when we are going to work through the problem and go through the code. So how did I, kind of stumble upon them? And back a couple of years, I was working in a game studio. We were developing a game, and we encountered this problem. So we had these game entities. You could think, I don't know, like planes or cars or spaceships, anything like that. And these entities, let's say cars, they were assembled from
multiple parts. So you would have separate resources for wheels, for the body of the car, for the headlights, for maybe the driver inside the car, maybe some bodywork, stuff like that. And we had all of those resource files, and then we had a pretty elaborate algorithm how to actually assemble the car from all of these parts. And you can swap out one set of wheels for another set of wheels and kind of put some tags on the car and stuff like that. And we had two cases. One of the cases was that we needed to load it, assemble the car asynchronously. So imagine you have this menu of your garage or something, and you're just scrolling through it, and it would be very bad if it would stop the game while the car is loading. And the cars, they load from disk. It's not an instant process. You cannot preload all of them, so it takes some time, basically what I'm trying to say. And when you scroll, you want to for that to happen asynchronously in the background, and until the car is loaded, you show some sort of spinner that is there to indicate that, yep, still loading. And another case that we had was kind of an anti-case of that, which was the synchronous loading. We had a couple of places in the game where we needed to stop the game and could not allow the game to actually run until the car was loaded. And if we did it asynchronously, then everything kind of broke down. So the problem is this: you have this algorithm that assembles the car, and you have two cases. You have the synchronous case and you have the asynchronous case. And you don't want to rewrite the algorithm and maintain two versions of it. You kind of want basically to have the same algorithm, because the only thing that really differs between two cases is the wrapper type of the data. In a synchronous version, it is a task. In the synchronous version, it is basically just you could say, an array of one element. It's just a box around the data. And I'm gonna explain why that is important down the line. So that's the premise. That is how we ended up with a solution that I'm gonna show to you.
and let's get on with it. Um, any questions before we move on? If not, let's dive into the code. So the code, I have already prepared all of the code beforehand, so I'm just gonna go through it. We're not gonna do live coding. And basically what we have here is, so we have basic building blocks of the code. So one thing is we have a resource ID, so you could think of it as, you know, a file name or maybe an internet address or something. So an identifier that would say, oh, this is wheels, or this is that, or this is something else. And then we have something that is resource data. If you are wondering what the record thingy here is, I'm using .NET 5 and the latest C#, which is C# version 9 right now. So a record is just a class where this becomes the constructor, and this field is read-only, or multiple fields. And it also generates toString and hash code and equals methods. So we have the resource ID and we have the resource data. And now we're gonna go and implement this loader. Well, it's not gonna be a real loader, but we're gonna do a bare bones loader. So here we have some way of loading the resource, which is basically you pass in the resource ID, and then you get an asynchronous task that eventually returns the data for the resource. And then you have the method that kind of assembles the car, assembles the entity. And in our case, you just pass a bunch of resource IDs into it, and you give a loader. And then, you know, it would do something with those things. But in our case, we're just gonna start loading all of the resources in parallel at the same time by turning this into an immutable dictionary. And here we can see that, you know, it's an immutable dictionary where the key is the resource ID and the value is a task that will eventually produce the data. Now when we have the dictionary, we kind of need to transform, like extract it or wrap it out or aggregate it, how you want to call it. But basically, instead of having a dictionary out of many tasks, we need to have one task that produces a dictionary with all of the resources once that's finished. So we do that exactly here, and we're doing that. There's actually two ways to kind of do this. I'm going to show you both. So one is we do it, we create an immutable dictionary builder, and then we say, okay, so let's go through all of these tasks that are in progress, and let's wait until each and every one of them finishes. We get the data, we stick it into the dictionary. Once every task is done, we just turn that into immutable dictionary. The other way essentially kind of does the same thing, but you can express it not with imperative code, which goes for each. You can express it via link queue. So you start with a task that is already completed, and it has this immutable dictionary as the result. And then you kind of join together this task that provides the current results and the task that is actually loading the resource data. And then after you have both of them, you add the loaded data into the dictionary, and you have your new result, and you pass it here, and basically this kind of chains everything together. So
pretty much, I would say this one is actually easier to understand, but we will need something similar to this a bit later down the line. So I'm kind of showing that it is possible to do it in two ways. So far so good, right? We have a way to asynchronously load these resources, and we're happy with that. Now, what do we do when we have synchronous resource loading? And the synchronous resource loader is a bit different from the synchronous one, because a synchronous one returns a task, and the synchronous resource loader just returns the data. Maybe, as if it doesn't take any time. So maybe the data is already in the memory, or maybe it's very fast, or maybe you just need to block the thread when loading those resources. So whatever the reason, we have a synchronous resource loader here. And we really want to reuse this algorithm instead of, rewriting it. So here we can sort of do it, and we can kind of trick the code that we wrote and turn an asynchronous resource loader, synchronous resource loader, into an asynchronous one. So we can say, when we get an ID, load it with the synchronous loader, and then let's pretend that it's a task. It's a task that is already completed. And here we also get a task, right? Which says, oh, so this is asynchronous, but we say, oh, but I already kind of know that this thing is always, it just pretends that it's asynchronous, so we can invoke result on it. Now there's a couple of problems here, or I would say maybe not problems, but landmines that lurk you in the future, and it's gonna probably explode later down the line. And the problem is that now this method is really reliant on the internals of this method. And what do I mean by that? So basically, when you call this, if the task isn't completed yet, then it's gonna block, right? And you might think that your sync resource loader, for example, always returns resource data very fastly, very quickly. But maybe later down the line, some other developer came and said, oh, so we're doing asynchronous resource loading, so maybe let's add analytics, right? And he would go into this method and he would change it so that for every resource that you load, you would send, for example, a query to the analytics server, or maybe some other thing network related, because everything's asynchronous, right? And then this suddenly turns from fake asynchronous into real asynchronous. And maybe previously your synchronous resource loading took, I don't know, 20 milliseconds. Now it takes 20 seconds, which is a breaking change and a very bad one. And it is a change that is very hard to actually catch with unit tests, because when you're writing unit tests, you're usually kind of writing stuff for, well, correctness and the results, and not timing of how long things take. And there's also even another case. So imagine that our resource loading is not only synchronous, but maybe optional. So you might not find the resource that you're trying to load. And to represent that, we're using the option type. And for that, I'm gonna kind of move away a bit from this and into what an option type is, for those that do not know.
So an option type is basically just data structure that replaces nulls for reference types, or system nullable, which works for value types. So our data structure works for both value types and for reference types. Value types are structs and integers and characters, and reference types are classes and strings. So basically, option has one of two cases. So it either has no value, it represents kind of null, or it has some value and it's not null. Sorry?
Yeah, sorry about
Yeah, we had some noise there. So yeah, and it's really simple. So it just has a boolean inside of it that says, whether there's a value here or not. And if there's a value, we store it in this field. And if there's no value, then it's gonna just be a default value. So for integers, that would be 0. For strings, that would be null. Therefore, it's named unsafe because you might access it and it's actually null. So basically, our optional resource loader says that this resource data is optional. You might not find it. And again, we don't want to rewrite the algorithm. We want to reuse the asynchronous resource loading. So how can we do that? Again, we kind of can by pretending that we are asynchronous by returning a task. And we can say, okay, so let's try to load it. Let's try to see if it is a sum case or none case. If it is a sum case and we have the value here, then let's pretend that it's a task that is already completed. Otherwise, let's kind of create an exception and say that yep, this failed. And here we get a task, but now we kind of have to check because we have to return an option. And we check whether it actually completed successfully. If it did, we return some. If it did not, we return none. However, this also has like an edge case. So now this code expects that the only reason why this task could fail is because of this, right? But to be truthful, there might be other reasons why the task might fail. And again, we're depending on the implementation of the asynchronous load resources and the inside of it to kind of, that this method, it says I'm working with a task. I can do whatever the task, supports. And it might fail for other reasons. And then when a failure occurs in the task, we just say, whoops, no resource. Even in fact, however, there might have been a failure where there was a resource, but it couldn't be read because there's no permissions or something like that. So that's the problem that we have. We kind of can try to shoehorn all of our different use cases, the synchronous loading, the asynchronous loading, the optional loading into one case, which sort of supports all of it. But at the end of the day, you might even encounter something that task has no innate capability to support, something that is very custom and you can't really express in terms of task. And then you're sort of screwed. And you have to modify the algorithm and have a duplicate for another data structure. So the solution to this problem is higher kind of types. Before we move on, is there any questions? Nope. Okay. So how does the solution look? And the solution is to kind of have this. Basically, if we look at it, at all of these cases, you can see that the resource loaders, they all kind of look sort of the same. And, you know, they take in the ID and then they return the data wrapped into some box. Okay, and in this case the box is task, in this case the box is option. In this case you would say, oh, there's no box, but we can kinda do this thing called ID. And ID is just a really simple box. It's just a structure where, you know, it has one value, one field for keeping a thing. And the ID stands for identity. So you can also kind of say that, yep, this is also a box. We can do this and, you know, works fine. So we can see that the inner type is always the same, but the outer type differs. And the higher kind of types allows you to abstract away this outer box. So you can think of it as, you know, if you have, for example, if you have generic types, the task is generic over T result, type of the result, and you don't know what the result type will be. And we specify that it will be resource data here. So higher kind of types kind of allow you to be generic over the outer layer of the generic thing. So to see how that looks like, let's go to our solution. We say that we have a higher kind of resource loader, which returns this weird type with these two generic parameters, and one of them is called witness. So let's go and see what this is about. So higher kind of type is just an interface, which takes in two generic parameters and does nothing with them, sort of. And the witness is the generic parameter that specifies what kind of box are we in. The witness is, you can think of it as the type doesn't do anything on its own, but it witnesses that we're gonna be, you know, boxing it. We're gonna be using a box of a task, or a box of an option, or a box of an ID. And the element is gonna be specifying what will be inside that box. So it's gonna be result data in our case. So for example here, a high kind of type where the witness is this type and the element is this type represents an option of integer type. And why is it called higher kind of type? So it is a bit of a mathematical term, I would say, but the first order types are like the regular types that you encounter and use often probably in everyday life, where you just have, you know, a list of something, and you can kind of think of it as having a signature where you say, oh, so I have a list, but I don't know, you know, or an option where I don't know what the A is yet, and then I give a type, I put it into that slot, and the actual kind of notation that you can see in a lot of places is
by using these asterisks, which is a bit weird and complicated in my opinion, but it is what it is. But the idea is you put a type like an integer into the A slot, and then you get a proper type which you can use then, like an option of integer or a list of integers or a task of integer. The higher kind of type, you can think of it like there's two slots. There's the outer slot F and there's the inner slot A. And the idea is that you first give a type and that produces the first order type. So for example, if you take a type like option of A, and you have to make sure that the amount of generic types matches. So this defines a higher kind of type which takes one generic type. An option is also such a type. So another type that you could pass in would be, for example, like function of A, right? Or maybe action of A. However, if you try to pass in function of, let's say, A and B, that wouldn't work because the amount of slots wouldn't match, because this has two slots and this only has one slot. So you take that type and you put it here, and you get a first order type like option of A, and then you take another type and you put that into the slot, and then you actually have the concrete type, which is option of integer. So I guess that feels a bit complicated. So any questions here? If not, let's try and see how that works. So now our load resources method, it takes in the resource IDs as previously, takes in the loader as previously, but it also takes in this thing called monad, and it returns now the higher kind of type where the element is the immutable dictionary. And basically we do the same thing. I've expanded the type here so it would be more obvious. So we start loading all of the resources and we just go through the IDs and we turn that into immutable dictionary, where the element type is this higher kind of type. And now we need to wait until all of the resources are loaded. And this is why I showed you the original version aggregate 2 here, because we can't await on the higher kind of type because we don't know what it is. We don't know if it's a task, it may be an ID, it may be something else. And this is where the thing called monad comes in. And the monad is basically just a data structure that defines operations that you can do on that higher kind of type. So there's a couple of operations, and a monad is an interface which says, oh, I'm gonna provide the operations for the option type or the task type or the ID type. And these are kind of the mathematical terms from this branch of mathematics called category theory. People kind of learn them, and if you ever wondered what a monad is, you're kind of gonna get an explanation what it actually is, and it's fairly simple. It's not gonna be a full explanation, but it will be. So basically what a functor does is a functor provides a select operation, the same select that you would get from LINQ. So if you do list.select,
you you give it a list and you give it a function and it applies that function to every element in the list. So this essentially does the same. And another operation that the monad provides is the wrap operation. And the wrap operation, what it does, it basically you give it a value, like let's say 42, and then it wraps the box around that value. So in our case, if we try to wrap 42, it's gonna just return some 42. If we have a list and we wrap 42, it's just gonna provide a list of one element with 42.
Arturo, I have a question.
Yeah.
That select is the same as map in other languages?
Yes. So the question is whether the select is the same as map. Yes. In other programming languages, it's often called map. I chose the word select because LINQ in C# uses that method name.
And the wrap is the same as lift in other.
Yeah, it's the wrap. So the question is whether the wrap is the same as lift, and yes, the wrap is also. So this is funny because there's multiple names for the same function, and some call it lift, some call it point, some call it pure. So, and for me, that best name that kind of makes sense is wrap, because you kind of take something and you wrap the box around it, or you put it in the box. And then there's another thing, which is select many, which is known as flat map or bind in other programming languages. So the only difference is that the mapper function, the only difference from the select is that the mapper function in select, it just maps from one value to another value, whereas in select many, it wraps from one value to a higher kind of type of another value. So it's the same thing as in LINQ select many. And in other languages, like Scala, this actually kind of is expressed more elegantly, maybe. So for example, the functor would be defined like this. You would say there's a trait, which is the same thing as an interface, only of a different word, functor. And instead of providing this witness type, you would provide, say, I'm gonna take in a type F that's gonna have one slot. And this is then native support for the higher kind of types in a language like Scala. And then, instead of select, having this kind of convoluted type signature, you would then have this type signature where you would say, there's generic parameters from and to, same as here. And there's a value higher kind of type of from, but instead of saying, this, instead of using this witness type, you would just say, it's this box F, and inside of it, it's gonna be an element of type from. And we're gonna have a mapper, which is a function from to to, which is the same thing as we have here. And then it's gonna return a box with the to element inside of it. So the same thing that we express here, only here we kind of have to, because C# does not support it natively, we have to kind of fake it. So let's get back to this. And here, what we do is,
here we have this immutable dictionary where the values are, inside these higher kind of boxes. And we need to somehow join all of those boxes into one large box to return that. We need to return the higher kind of type of a dictionary, whereas here we have a dictionary of higher kind of types. So how do we do that? So we do that essentially by using the aggregate 2 version of the previous code. We start with the immutable dictionary, which is empty, and then we wrap it into that box. I've written these helper methods here, which allow you to kind of flip the order around, and instead of calling wrap on the monad, you can call wrap on the element. So it provides a more readable API in my opinion. So you start with this empty dictionary, and then you say, okay, so this is the dictionary that kind of represents the current datas. And here we have the key value from this dictionary, where the key is the ID and the value is the resource data, which is also wrapped in the higher kind. And then we have to join it. So we say we extract the dictionary by using the select many method, and we use select many here because here we're not returning just a value, but we're returning a higher kind of value. And then we do another layer of unwrapping, this time on the resource data. So we get the resource data here, and then we say, okay, we have a dictionary, let's add another element into it, which, because this dictionary is immutable, produces another dictionary. And in such a way, without ever knowing what the box type is, and only knowing that it has these three methods, which is wrap, select, and select many, we can write an algorithm that does the required things for any type that supports these operations. And if we needed something else for our loading logic, we could also write other interfaces in similar style as monad and add other operations, which then would define how to do things with this higher kind of type. And when we have this, the three versions that we had, the synchronous, and optional, look very, very simple because they basically just invoke the same load resources. They provide a higher kind of type resource loader. So this already returns ID now. They provide the higher kind of type boxes around the things, and then they provide the monad instances. So basically the definitions on how to do stuff with the higher kind of types to the load resources method. Now there's the important part. What is this narrow kind? And what is the witness type actually? So I mentioned that witness types aren't actually used and they're only useful in witnessing stuff. So let's go inside of this definition of the monad and see how it actually works. So the monad is we just implement the interface for a witness type. And the witness type is just an empty type, an empty struct,
we're never gonna instantiate it. We're never gonna create it. It only kind of is useful at the type level, so for the compiler, but not during the runtime. And what we do is we define the monad for the witness type, and this witness type should always only be used with the ID structure. And here we say that the ID implements a higher kind of type where the witness is this. So in theory, we could specify maybe option witness or something else, but that would be a bad idea. The whole idea of a witness is that only the data structure that you're implementing the higher kind of type for uses that witness. So the only use site of it is, well, where it extends stuff is here for the ID, and it no other data structure uses that. And what that allows us is it allows us to have this method called narrow kind, which says, okay, if I take in a higher kind of type where the witness is this witness, this specific witness, I can rely on the fact that no other type uses that witness except the ID type, and then I can safely downcast into the ID type. Because normally, when you have an interface, that interface might be implemented by many different types. And this witness kind of proves that it is, in fact, that the real type behind this interface is in fact ID. And then we can be 100% sure that this operation will never fail. Does that make sense? I guess it is a bit weird, but maybe let's move on and see if that works out or not. So when we provide the monad instance, we define a class monad which implements the interface monad, and we have this. It defines that monad instance for this particular witness type. Then we say, okay, so what does it mean to wrap an element? So for ID, it's very simple. We just create a new ID, and we pass the element inside of it, and we return the interface, where the witness type is the W, and the element is generic. So what does it mean to do select? So here we get higher kind of type of from, and then we can safely invoke this narrow kind method and turn that from the higher kind of type into the concrete type, into the struct of ID. And when we have that, we can pass that into the mapper, and I guess we can do this, but I've also written these two implicit conversions from ID into the value and from value into ID to kind of make it more ergonomic. So you pass that into the value, and then you get a result, which is of type 2. And then you just wrap that back into a box. And that's what the select operation on ID or map operation on ID is. And select many is even simpler. So we basically do the same thing. We narrow, kind from the higher kind of type into the concrete type, and then we pass that into the mapper, and the mapper already returns the higher kind of type. Therefore, we can just return it here. Then we can see what does it mean for the option class. And for the option class, if we wrap something, we just return a sum representing that there is a value there. If we do select, the same pattern. We narrow the kind, and then we can invoke the map operation, which is defined on the option. And the map operation is pretty simple. If there is a value,
pass it through the mapper, and return a sum. If there was no value, then it means we don't have anything to map and just return no value. Same with select many. We narrow the kind, and then we do the flat map operation, where we pass the flat map. This is again pretty much the same. If there's a value, we pass that into the mapper, but this time the mapper returns an option, therefore we don't need to wrap it again. And if there was no value, then just don't return anything. Well, return a none, but which indicates no value. So here we pass this from into the mapper that returns a higher kind of type flow. So we need to narrow it down again, because this expects an option. So if you erase this, it's hard to see, but this part becomes squiggly where the flat map is. So it says, that basically it doesn't recognize the type. So it would be even possible to do the narrow kind operation automatically, as we do have here with these implicit conversions. Unfortunately, C# does not allow us to do implicit conversions from interfaces. So we have to do it explicitly. And for the synchronous loader, we have the loader, which returns the task type from the .NET standard library, which does not know anything about our higher kind of type thing. So we have to use the adapter pattern and wrap it into another class, which I call higher kind of type task, which just implements this interface. And again, the same thing, we have the witness type, we have the narrow kind thing, which does the casting, we have the monad instance, we have the wrap, and to wrap an element, we say, oh, it's a task that is already completed, and we wrap that into the higher kind. If it's in select, we narrow it down to the higher kind of type, the specific class. Then we await until the task is finished. Then we pass that into the mapper. Then we return the value, and we get a task here, and we wrap it back again into the higher kind. For select many, very similar. Narrow it down, await until the from value is available, run it through the mapper that produces a higher kind, so we have to narrow it down, await until the to value is produced, and then return the to here. And then we need to wrap this task into the high kind. So what are the advantages of using higher kind of types? So the first advantage is that load resources cannot do weird stuff. It can only do, because it doesn't know anything about the type, it doesn't know in what kind of box it is, it can only do the operations that you allow it to do by providing this monad instance, or whatever interface you might write, and you know for 100% that nobody will ever come and add some code in the future that will do something unexpected and break these methods. And if they come and do add something, like they maybe add another interface here, or they maybe go and change the monad interface and add some methods there, then they will be forced to provide, either if they added another interface, they will be forced to provide instances of that interface here, where you actually call this code, or they will be forced to go here and provide additional methods in the monad implementations. Therefore, there is no risk of your code just silently breaking and doing the wrong thing. So it's you get a guarantee from the compiler that this code, once it's written, it will not break. And it's not a guarantee that is provided for you by unit tests. It is a guarantee that is provided for you by the type system, by the compiler checking it every single time you build your code. And it's impossible to build broken code in such a way. So that's the main thing. And yeah, that is it. So, any questions?
Yeah, Arturo, very good stuff. Really awesome. I was actually.
Sorry, might I record your voice into the stream? So wouldn't will that be okay?
Yeah, that's fine.
Okay, so desktop audio is now being recorded. Okay,
Yeah.
so what was the question?
Yes, actually, it was kind of answered, but I just want to kind of make it clear. So when looking at option and ID implementations, the witness itself was inside of these classes. So I was wondering, so that means that to implement the kind of to write the higher kind of type implementation and the witness, I actually need access to ID and option code. And then I was wondering, like, how is it going to be possible to implement higher kind of type for something that already exists? But then you showed it in the higher kind of task implementation that you actually need to write a wrapper for every type for which you want to implement higher kind of type, right?
Yeah, that's the unfortunate, you could say, side effect.
Mm-hmm.
This struct can be anywhere. It doesn't matter really. I just put it because it's kind of convenient and nice to write it in such a way, so it's the witness for ID. But you might as well do something like this, like IDW, and it's the same thing. The important thing is that the witness type should be used only for that
Yeah.
for that type. So you could write the narrow kind. In fact, the only reason why we need a witness type is to be able to write a narrow kind method that would know that it's 100% safe to cast this interface into a concrete type.
So, yeah, so then I wonder, would it be possible to implement this not as a type parameter to a higher kind of type class, but just as a kind of a specific class that extends from higher kind of type, and then you would also know that you can cast the specific one back to ID. Probably it wouldn't be as nice, but it would still work without the witness then.
I'm not sure. So I might have lied a bit because the witness is also needed here. So all of the monad instances and functor instances and everything, they are provided for a specific witness type.
Yeah, yeah.
So I don't think there's a way to kind of the whole idea of the witness type is the witness simulates the syntax that you would get in another language, kind of built in. And here you kind of hack the type system a bit and use it in a clever way to simulate the same effect.
Yeah, good stuff. And probably there is no limitation on the number of. So you had an example at the beginning where you kind of talked about higher kind of types, and you had an example where function with two type parameters doesn't fit a hole with only one type parameter. But with this witness scheme, it would be also possible to implement higher kind of type with, for example, two type holes, right?
Yeah, yeah. You would probably need like something like this. So you would need an separate interface for every arity of holes that you have. But with that, it seems to scale perfectly.
Yeah. Yeah, yeah, looks good.
Okay, we have Silvertoad asks, so do in this case we express the box type where we load stuff and result type in higher kind of type? I'm not sure I understand the question here. Could you expand on that? Okay, Silvertoad is typing. Oh, I already cleared it later. Okay. So, is there any other questions? If not, I guess we're done with this topic, and I'm gonna upload this to YouTube later. So if there's questions, you can ask on Discord or maybe in YouTube comments as well. And I'm gonna upload the code for this to GitHub, so you can clone it and play around with it. So yeah, thank you for your time. I hope this was informative and useful for you. It is not my I did not come up with this trick. I found it on the internet, and originally I found it for Java, so you can use it for pretty much any language that supports generics and interfaces. And it is quite a useful trick, I would say. It's a bit noisy, but what you gotta do, you have to do what you can. You have to, if you need it, it's really useful to be able to do this. Okay, thank you, and bye-bye.